So now what we like to do is to find the derivative at c, we have to compute this limit of difference quotient. But we don't want to do this each time. So if possible, we want to develop formulas for future work. So first of all, symbols. So f prime at x is equal to, we write that as derivative of f with respect to the variable x. Derivative of f with respect to the variable x. So we write that as df dx, or we can write that as big df, derivative of f, or we can put formula of f there, or since y usually is f of x, y is the output when we plug in input x to the function, so f prime of x is sometimes written as y prime, or it can be written as dy dx, derivative of y with respect to the variable x. So all these mean the same thing. Okay, and we'll use this interchangeably. For example, a d dx of k. So that is the formula. F of x equals to k. That's the formula. So it is the limit at any x. So limit as h approaches to 0, f of x plus h minus f of x over h. That was the derivative. But my function is constant function. It is k at every x. So as I get close to x, my slope of the tangent line is 0 because the tangent line itself is just a horizontal line. So the derivative of constant function at any x is 0. The derivative of the function x to the n with respect to the variable x. So again, that's the formula of the function where n is a positive integer. So n is like 1, 2, 3, 4, etc. Okay, so what's the derivative? Well, let's recall x to the n minus c to the n. So then it is x minus c times x to the n minus 1, c to the 0, plus x to the n minus 2, c1, plus dot dot dot, x to the 0, c to the n minus 1. Right? It can be factored like that. So derivative, so that is derivative of the function at any x where f of x has the formula x to the n, right? So that is limit h approaches to 0, f of x plus h minus f of x over h. So if we plug in the formula for f of x plus h, it is x plus h to the n minus x to the n over h. Okay, so we'll apply this fact to here. So if I have something to the n minus something to the n, then it can be factored like this. And I have something to the n minus something to the n. This is true when n is a positive integer. So this is limit h approaches to 0. I have h in the denominator, so something minus this. So I can think of this like A and B. So that's A and that's B. Okay. So A minus B, and then times x plus h to the n minus 1 times x to the 0 plus x plus h n minus 2 x to the 1, and then plus dot 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 x plus h to the 0 x to the n minus 1. So that's what we get, right? And the first term, x cancels out and we get h. Then since h is approaching 0, h is not 0, so I can divide h and h. Then what I get is a nice polynomial. X is fixed. X doesn't move. What moves is h. So you can think of x like number 5 and h is what is moving. Then we get a polynomial in terms of h. And polynomial is continuous everywhere. So to compute the limit, we can do direct substitution. Then we get x plus 0 n minus 1 x to the 0 plus x plus 0 to the n minus 2 x to the 1 plus dot 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 x plus 0 to the 0 x to the n minus 1, right? So these are nothing but x. All these are x. And when I do this, I get x to the n minus 1 here. When I combine them, I get x to the n minus 1, same thing here. And how many terms do I have? Well, if I look at the power of this, it starts at 0 and it ends at n minus 1, so there are n terms. So we're adding n terms of x to the n minus 1. So all of that becomes n times x to the n minus 1. So f prime of x, when f of x is x to the n, where n is 1, 2, 3, 4, etc., then we get the formula that it is n times x to the n minus 1. So that's very important. This came from this part, and that part remains alive when n is bigger than or equal to 2, because if n is 1, then we don't have this part, right? So that is true for n equal to 2, 3, 4, etc. Now when n equals to 1, we can prove directly when n equals to 1, f of x is x. So at any x, f prime of x is limit h approaches to 0, f of x plus h minus f of x over h. F of x plus h is nothing but x plus h, and f of x is x. So when we subtract, x disappears, and since h is not 0, we can divide top and bottom. So we get 1. Hence, so f prime x is 1 for all x. So when we combine this and this, now we want to write this as a general rule. So if n is 1, it is 1 times x to the 0. Then if x is not 0, then x to the 0 is 1. So it will be 1. If x equals to 0, we are getting into the problem because 0 to the 0 is undefined. So if I write d dx x to the n is n x to the n minus 1 as a general rule, then I encounter a problem when n is 1 because at x equal to 0, this formula becomes undefined. Whereas at x equals to 1, I still have the derivative. So to denote the general power rule for all positive integers, we assume 0 to the 0 as 1, and we write this general rule. So we can say this is true for all n positive integer and for all x. So in the previous proof, n was positive integers, but we'll generalize n to a real number. And for the real number, the proof will come later. Okay, so for now, just accept that when n is even a real number, the derivative with respect to x of x to the n is still n times x to the n minus 1. Okay, so just accept it for now and we'll prove it later when n is any real number. N is real. So for C, so e to the pi is a real number, right? Therefore, the derivative is n times x to the n minus 1 is the derivative. And what's e to the pi? E to the pi is exp of pi, right? What was exp of pi? It was the inverse function of ln. So the graph is like this. That's exp of x, which we defined as e to the x. So pi is some number, some real number, and here's the e to the pi. How do we find this number approximately? It will be given in the Taylor series later in Calculus 2. And the derivative with respect to e to the ln pi. Remember, it was d dx x to the n, where x is a variable. Okay. Here, e to the ln pi is nothing but pi. So this is actually d dx k case, constant function case, and the derivative is 0. Number 5, theorem. If f and g are differentiable as c and k is a constant, then blank and blank are also differentiable as c. So, what does this mean? Yeah, it means the function g of x is k times f of x. constant multiple of a function, and we want the derivative of g as c. That's what it is. Yep. So it's the limit x approaches to c of gx, where g is this, minus g as c over x minus c, which is limit x approaches to c, k f of x minus k f of c over x minus c. And since k is common to both, we can factor this as limit x approaches to c, k times f of x minus f of c over x minus c. So we have a limit of constant multiple of a function. If I think of that as a whole function, then can we use limit law? Yes, we can, because I know that this limit exists, f prime c, because we assumed that f is differentiable as c, so I know that f prime c exists as a definite number, so I can apply limit law here. Limit of constant multiple is constant multiple of the limit of the function. So that is this. And since this is nothing but f prime of c, I can write it as k times f prime of c. So what we have achieved is the following. If I have constant multiple of a function, then the derivative as c is nothing but derivative of sc computed and then multiply the constant. So kf prime sc is k times f prime of c. So this is constant multiple rule. So if f is differentiable as c, then kf is also differentiable as c. So the first blank is, if f is differentiable as c and k is a constant, then k times f is also differentiable as c. For the second blank, let's look at the sum. So the derivative of f plus g at c is limit x approaches to c. My function is f plus g of x minus f plus g as c over x minus c. So how do we compute the value of the sum of two functions? You take the value of f and take the value of c, and then you add them up. That's the definition of the sum of the two functions at a point, right? So this is fx plus g of x minus, this is f of c plus g of c all over x minus c. And then this is limit x approaches to c. Now I can combine f together and g together. Then I get f of x minus f of c, and then plus g of x minus g of c. And then I can give x minus c as its common denominator. So I can write this as a sum of two fractions. So I have a sum, limit of the sum. Can I apply limit law? Yes, I can do that, because each limit exists. First one is f prime c and the second one is g prime c. Because our condition, our assumption was that f and g are differentiable as c. That meaning I have f prime c, definite number, g prime c, definite number, right? So going back to there, we can apply limit law, and limit of the sum is sum of the limits. Limit of the first one plus limit of the second one. So here is the sum rule. Sum rule. Derivative of the sum as c is nothing but sum of the derivatives at c. Okay, so memorize this.